All right. Let's get back to our seats. I know Walter is in high demand right now. Awesome. All right. So we got Dmitry with the after lunch talk. This is the hardest talk of any conference. And people have difficulty staying awake. And now they kind of feel better, the digestion process. I shouldn't talk about this, right? This coming talk is of special significance to me personally. I've known Adam for more than 4 years since I joined Facebook. He's a senior engineer, and he's done he's worked on a number of highly impactful projects, both internally and externally. And he's always been he's taken nicely to the opportunity of using D. And finally, the day has come when I saw, a diff by him written in D language, and I was very glad to do so. And so, Adam, take it from here.
Cool. Thanks, Andre. I'm going to talk a little bit about some of the ways we use D at Facebook. And one of the most important things for us is using D together with C++. So you may have heard that Facebook uses a lot of PHP, and that's all on our front end. On the back end, we're largely a C++ shop for all of our backend infrastructure code. We've got a lot of other languages in play as well. But historically, for a long period of time, the majority of our backend infrastructure code has been in C++. So being able to use D with a lot of our existing C++ code is pretty important to us. So I'm going to talk a little bit about why it's important for us to be able to use D with C++. I'll recap a little bit about calling C code from D, which I think a lot of you are probably already familiar with. D has pretty good support for calling C natively right out of the box. And then I'll talk about some of the things we're doing to call C++ from D. And I'll talk a little about tools, some of the tools that exist to be able to call C code, some of the tools that we'd like to have for calling C++ code, and some of the future directions and things that we think could be done to help improve the compatibility with C++. So first, let me get a little bit of brief history about the usage of D at Facebook. So like I mentioned, that we're largely a C++ shop on our backend infrastructure. Back in 2009, Andre joined Facebook and started preaching the gospel of D and trying to convince all of our C++ developers to use D and telling us how awesome it was, how many more features it has, and why we should all be writing our code in D now rather than in C++. So this is great. A lot of developers, are like, yeah, this feels like C++, and they fix lots of things. But nonetheless, a lot of developers, including me, for the most part, just kept banging out code in C++. Even though Andre's over here saying, D is so much better, look at all these cool things you can do with D, a lot of us still kept writing in C++ mostly. And the one main reason for this is library support. So we've got a lot of infrastructure code already written in C++. And so if you're a developer here at Facebook and you're starting a new project and you're trying to decide what language you want to use, if you build code in C++, there's a lot of stuff that you get out of the box. That if you're trying to build a new project in D, there's a lot of stuff you're going to have to re-implement. So some of the libraries that we have in C++, we've got really good statistics libraries. If you start a new service, you're going to get a lot of statistics out of the box about how many requests per second is your service doing, how many errors are you serving, how long does each request take, how much time are you spending doing network I/O processing versus the actual processing of your requests that you care about. And a lot of other abilities to define your own new statistics as well. You get a lot of good configuration libraries for how to configure your service, how to push configuration out across many machines and detect when there's a new configuration for you. A lot of high-performance network I/O libraries for doing highly concurrent I/O processing with zero copy and low overhead. Authentication support, if you want to have services authenticate to your service. High-performance distributed data structures, libraries for accessing a lot of the different data storage tiers across Facebook, and libraries for helping you implement distributed services that are sharded across many different servers. So there's a lot of stuff that's just there for you by default if you end up writing code in C++. So there are a couple options here. we could decide, hey, let's go re-implement all these functionality in D and have nice native D bindings for all of these things. It's a little bit infeasible for us, though. We've got a lot of developers who've already invested a lot of time building up all these C++ libraries, and so there's a lot of work to redo in D if we went down this path. And the C++ libraries are still improving. They're a moving target. So even if you started out and you built a D version of some of these libraries, the C++ versions are continually improving, and then any new feature that you implemented that got implemented in C++, you'd have to port to D every single time. And also, in terms of developer motivation, you have to find the developers who would then implement these native D libraries. And like I said, for most developers, if they're building their service, they care more about, I just want to get the code to get my service done. I want to build the code that's key to my service and not all the support code that I could get for free if I was in C++. So that's a lot of the reasons that making sure we have good C++ integration and good C++ compatibility is really key to making sure that D continues to ramp up and take off and get used more widely here at Facebook and likely at other places as well. So given that we've established why we think it's important to be able to call C++ code, let's talk a little bit about how we actually call native C and C++ code. There's two main options. One being remote procedure calls, where your D code and your C or C++ code actually live in totally separate processes, whether or not they're running on the same server or not. And then you do all your communication between sockets. So that's one option. And D has built-in support for COM. Thrift is the RPC mechanism we use widely here at Facebook. And there's Thrift support for D that was also done as a Google Summer of Code project in 2011. Or there's native linking. And so this, in the native linking model, your D code and your C++ code live together in a single binary, and you can just call directly between the two of them without having to go through this remote procedure call operation. So I want to talk mostly about this native linking aspect for most of the talk, but I do want to say a couple things about Thrift first. And just to give you a little bit of background about the way Thrift works, like I mentioned, you have two separate processes, your D code in one process, and your C++ code in another process. Or if it's Thrift, it could be any other language, Java, Python, Ruby, Haskell, anything else that Thrift supports. And so you've got your native D data structures. And when you want to send them over to a C call to, say, pass them in as arguments, you end up serializing them. So they get serialized in some sort of byte stream that you can then send over a network socket, which then get reconstituted into C++ data structures on the other side. And then the reverse happens for your return values. So that's the main key piece of how Thrift works. The main thing is that all your data structures have to get serialized down into some wire level format and then unserialized on the return path. And the way this happens is you have your Thrift interface definition language file, which defines here are all the data structures that I want to be able to send back and forth between Thrift clients and servers. And the Thrift compiler then translates that Thrift file into native language bindings for D or C++ or whatever language you want to use. So the D Thrift implementation is a little bit different than most other languages. In most languages, normally, the Thrift compiler has all the code for how do we actually serialize your structure. So if you define a structure that has 5 fields, the Thrift compiler will generate native code for your language that says, OK, here's a native language structure that has your 5 fields. And when you want to serialize it over the network, here's how we serialize each of those fields. And for the most part, you then end up with these really long, massive generated C files, which have all the tedious, boring data of how do I take my structure and serialize it over the wire for all the fields that exist there. In D, it's a little bit different. In D, the Thrift compiler is actually really very simple, and the generated source files are also really very simple. They don't contain any of the code needed to serialize the data structures. They just contain the native D structures themselves. And then all the serialization logic is actually done in the Thrift library using compile time introspection and using mixins. So this is a very neat feature of D, that we can get away with having this really simple Thrift compiler. We have these nice generated source files that aren't horrible to go read. And instead, you do everything with compile time introspection. In practice, it turned out that there's a few downsides to this. I think Andre mentioned earlier that I hate mixins. I wouldn't quite go that far, but there are definitely some downsides here. So one of the things is definitely build times. This does make build time slower. That rather than paying the price of generating all the serialization code once when you run the Thrift compiler, you now have to pay the price of this for every single D file that you build that imports these generated D source files. So it makes build times a bit slower. It also makes things a little bit harder to debug. Hopefully, there aren't any bugs in Thrift and everything works well, and you don't ever have to go try and debug problems with it. But when there are problems, in other languages, you can step into the GDB in the debugger, and you might get spit out somewhere in this generated source file, and you're like, OK, I'm on line 12,001 of this file here, and I can go find out what that is. In D, you're going to get some source code and line number, and it's in the Thrift like codegen.d file, and the line number is sort of irrelevant and maybe off the end of the file because it's somewhere in a mixin which got generated. So that makes the debugging a little bit harder. It also makes the library a little bit harder to understand as well, because we've got a couple of files in there that are like 90% mixins for generating files. And actually, one of my first experiences with D, Andre gave me this bug. He said, here, this should be really easy to go fix. The Thrift tutorial is broken. It used to compile, and we imported some new code from Thrift, and now it doesn't compile anymore, and go fix the compile error. And it turned out to be some recursive invocation of a mixin trying to introspect a function that was calling the mixin being generated, which didn't exist yet, and really hard to track down in some line number that didn't exist. So it's kind of cool, all the stuff you can do with mixins. This might be a case where just letting the Thrift compiler do it might have some other benefits for us in this particular case. So that's all that I want to say about Thrift for the most part. For the rest of this, I'll talk about natively calling C and C++ code from D. So how many of you have called C functions from D so far? OK, so that's like the vast majority of folks. So everyone should be pretty familiar with this. The way this works is you've got a bunch of source files. Some of them can be D, some of them can be C, some of them can also be C++. You compile all of your source files. They all generate .o files. And at the end, we link them all together into a single binary. And this works because D is binary compatible with C. It shares the same ABI, the same application binary interface. So once we've built our single combined binary with all this code together, if we want to call a C function from D, all we have to do is we declare the prototype for it in our .d file. We say it's extern C, so it knows this is C linkage. I shouldn't mangle the name or do anything special that way. And then we can just call it directly. And this is just a really simple example of calling strlen. Presumably, no one really wants to call strlen from your D code, because we've got better versions in D. And you can do the exact opposite if you want to call a D function from C++ code or C code. So in D, when you define your function, you say, hey, this function is extern C. And then you declare a prototype for it in C. And it's really easy to call it. Everything works great. Similar story for structures. Everything just sort of works out of the box. If you've got a structure in C that you want to use in your D code, you define a compatible structure in your .d file. And the memory layout's the same. If I've got to create the structure in C and I want to give a pointer to the D code for where it is, everything just works because both sides know, hey, this is the layout of my B structure. There's a little bit of work that you have to do in some cases of trying to figure out, my car in C is a byte in D, and it gets a little bit complicated for what about clock T or various type defs in the standard library. But for the most part, everything works pretty well. So this is great, and we like this, and everything works really well. However, there are a few things to be aware of when calling C code from D. This does require that we duplicate all of our declarations for all the functions that we want to call and all the structures we want to be able to pass back and forth between C and D code. And all those structure definitions, we have to maintain them in sync. So if we have a struct foo that is defined in C, and we define the same structure in D, and then later on, 2 weeks from now, a developer goes and adds a new field in our foo structure in C, we need to make sure that we go and add that same field in the same location in our D version of the structure. So this does require a little bit more maintenance overhead. And if you happen to get it wrong, if that C developer goes and adds a new function in your C code, and he tests his C code and everything works fine, and he doesn't know you happen to have a copy of it over here in this D file, it's going to blow up in your face in really sort of annoying ways. It's not even going to blow up nicely. You're not going to get a build failure, because the C source code and the D source code are totally independent. Your C source code says, awesome, I have this structure. It looks like this. Your D source code says, great, I have this other structure, probably with the same name, and it looks like this thing. And they don't have no idea that there's this conflicting definition somewhere else. So your code links, your build is successful, everything goes great, you run your program, and if you're lucky, your program crashes. If you're not lucky, your program corrupts memory silently, keeps running on, and somewhere later down the road, you realize something's gone horribly wrong, and now memory doesn't look like what I expected it to look like. So this is a bit of a problem in some cases when you get things out of sync. So there are some tools to help with this that I'll talk a little bit about later. But this is one of those sort of pitfalls to be aware of. So that's the process for calling native C code from D. C++ is a little bit of a different story. The C++ ABI is a lot more complicated than C. We've got things like function name mangling so that we can support overloaded functions in C++. So that if I call a function foo with an integer, it's a different function than when I call foo with a character argument. I've got namespaces, which also affect function mangling. I've got virtual versus non-virtual class methods. So I don't just have simple structures. I have classes now, and those can have methods. And then the ordering of those methods affects my virtual function table layout. So if I wanted to be able to call those, I need to know exactly how my class was declared, what order the functions were in, and be able to match the same virtual function table layout correctly. C++ adds exception handling, which then affects how you invoke functions, the parameter passing, and what happens when an exception gets thrown, and how you do stack and winding, and all the stuff that we didn't have to worry about with C. And we also have things like templates. So I've got a C++ header file over here, and I have some templates. And if I want to use it, then I know at compile time, I go ahead and generate all that code for doing that. Which then requires that, again, you parse the whole C++ header file to figure out how do I instantiate that. So a lot of this just makes the C++ a lot more complicated than C. So D is ABI compatible with a subset of C++. So it supports a subset of it, but things that aren't supported are namespace support, although Andre has mentioned to me that there were some plans for, oh, yes, Walter. Oh, OK, so namespace support is in now, apparently, as of last week, according to Walter. So my slides are already out of date. Yes, Walter just mentioned that namespace support was pulled in last week. So yes, my slides are out of date already. So namespace support is there now. So we should clearly pull in the latest version of the D compiler and make use of this. Because I think namespace support will make a big difference for us right now. And I'll talk a little bit about that in a second. Other things that are unsupported are exceptions. The C++ exceptions are not compatible with D exceptions, so how they get thrown and stack and winding is not the same. There isn't support for templates. If I have a D function that wants to use a C++ template, there's no way for it to know, OK, how do I generate all that C++ code over there for instantiating this template? And there's some limited vtable support. So there is support for calling C++ pure virtual classes and being able to use those, that D interfaces can be compatible with C++ pure virtual classes. But once you start putting, if there's any sort of implementation or data members in your C++ class, as soon as it's no longer just a pure virtual interface with no data members, then there isn't really very good compatibility for that. So what does that leave us with? What's the stuff that is compatible? So yes, there's a question?
That's actually been implemented. Most of the data member stuff actually works now.
Sorry, if we can repeat the question.
Actually, you said that nothing outside of virtual functions really works. A lot of it actually does now.
OK, what are the other pieces that are working?
Static member functions, non-virtual member functions, member variables, static member variables.
I see. Cool. So this is the name mangling for those things?
Yep.
OK.
And ABI compatibility.
OK, cool. So there's a lot, I think, that sounds like has been implemented recently that we can start making use of. The lack of namespaces was one thing that was sort of holding us up because almost everything that we have is inside namespaces. which then means if I can't support namespaces, even though I can mangle my functions correctly, if I can't represent the arguments that are in a namespace, we can't use the name mangling. But that does leave us back to what is supported today. So we can call C++ functions that are standalone, that aren't class members, but apparently this is supported now. This is also out of date now, that aren't in a namespace, and that never throw exceptions. So adding the namespace support will help us out a substantial amount, but largely this does leave us with things that are standalone functions that still feel very C-like. But the good thing is that we can still do a lot with this. We can still build wrappers for a lot of functionality, even though we're not completely compatible at the ABI level. So a couple interesting things. I'm going to talk about how we actually do end up implementing this and how we end up building wrappers in D for a lot of different types of ABIs in C and C++. And some of this is sort of setting up for talking about the patterns that we use, because as we build bindings in C++, a lot of our bindings are manually written right now. There are a handful of tools to help you automatically generate bindings for C code. There isn't a whole lot for C++. But as we're going and manually building our bindings, there are a number of common patterns that we end up using. And so I think there's a strong possibility here to take this and then build tools that in the future we can generate automatic bindings for. Yes?
So how about the Swig?
Swig? Is there Swig support for? I see. OK, so I wasn't aware of Swig support. I've looked into, so we'll talk about some tooling in the end. So is the Swig support pretty fully featured?
I mean, I've used I was able to wrap big libraries like OpenCV or other stuff. I mean, but it could definitely improve with like the recent namespaces.
OK, cool. Yeah. So Swig is also a potential other possibility here. So the things that we're doing internally today in terms of calling C++ functions from C, we're using extra in C for pretty much everything and not a whole lot of extra in C++. So this namespace support will allow us to start using extra in CPP. But from the way we're building our wrappers, there isn't a huge difference to us yet. One of the things that extra in C++ will let us do, let us put our stub functions inside a namespace. Because right now, without namespace support, all of our wrapper functions that we end up invoking from C++, from D into C++, they're top-level names. So we end up giving them long, sort of ugly prefix names so that they don't conflict with anything. And they're a little awkward to use. So a lot of our wrapper functions from D into C++, they're a little bit ugly. And so we end up building higher-level wrappers in D on top of them. For a couple reasons. So because of the names, and then also exception conversion is required between the two languages. So when you call a C++ function, you need to make sure you catch any exceptions that it can throw and return that back in D so that your D code knows, hey, an exception was thrown. I need to rethrow this as a D exception. So the overall structure of all of our bindings that we have written tend to look something like this. We've got our native C++ code at the bottom, and our D code up at the top. And we sort of go through two layers of sort of like helper stub functions, one layer at the D side and one layer at the C++ side of things. So we have our C stubs that are global scope today, have sort of ugly names, and then catch the exceptions that get thrown, return them back to D so that D knows, hey, this was an exception result, not success. And the D wrapper function gets this result back and then rethrows the exception and provides a more native D-like API so that it doesn't look really ugly, so that you can use it and the top-level code up at the top here in the D can see an actual D class API that doesn't feel like some ugly C++ thing that I'm calling, or C-style global functions. And I'll talk a little bit about how we're doing our exceptions. And there's a couple of slightly interesting things here. So for exceptions, we define a CVP result class. And this is really just a small wrapper that contains either a successful result or an exception, plus a Boolean telling you which exists here. And the way this is done, we're using the structure binary compatibility here. So this is the data members inside our CVP results. In C++, it's a union of the exception information or the result and the success. Same sort of thing in D. It's also a little bit interesting that this is a template. And if you recall how I mentioned before that templates aren't really supported because you can't instantiate C++ templates from D, it does work correctly as long as you know the template's already instantiated by the language on the other side. So anytime I call a C++ function that returns an integer, I know that C++ wrapper has already instantiated CVP results of an int on the C++ side of things. And so my D code instantiates the D version of CVP result of int, and it ends up being binary compatible with the C version. So we are able to use templates as long as we know it's already been instantiated for us on the other side. And the other thing that's a little bit surprising here is we're calling these all through extern C functions. So we do have, even though the function's extern C, it returns a C++ template. But everything still sort of works for us. And this is just sort of the API for our CVP result class. The previous slide was showing the data members. On the API, in C++, about the only thing you ever care to do to a CVP result is construct it. And on the D side, we disable the constructor because you should never be trying to construct a C++ result from D code. All you do is you try and get their value out of it. So you can call check, which is just going to rethrow the exception if it was an error. And as long as the result was non-void, you call get to get the result out of it. So this means on D side, there's no way to get the result back without checking to make sure there was an exception and rethrowing the exception if there was one. So this lets us translate all the exceptions from C++ back into D. And excuse me. And we also have a couple wrappers on the C++ side of things to make this a little bit easier. So every time you implement a C++ stub function, you don't have to do this exception checking and creating a C++ result yourself. We have a little wrapper function that takes a lambda, and then it automatically catches any exceptions you throw, converts them to an appropriate CVP result, or takes your return value and constructs it into a CVP result. So this just makes the whole process a little bit easier for us, for developers that are creating bindings, of having this wrapper class and this helper code to do this for them. So that's a little bit about how we end up calling functions. When we need to wrap structures or classes, if I've got a class in C++ and I want to be able to use it from D, we tend to have 3 different types of ways that we will expose that class into D. And this depends on the class in C++. So normally, like I mentioned, these are manually written bindings. And so a developer who's building the bindings looks at each data type and tries to figure out, like, what's going to be my best option for how I wrap this data type. And these are sort of maybe an order of preference here. So in some cases, we'll define binary compatible structs, which works the same way it does in C, that as long as I define the structure the same way in C and in D, everything works. I can have pointers. There's very low overhead because my C++ code and my D code actually just point to the same object, and there was no real translation between the two of them. And this also works for class methods as well. We have a number of wrappers where they're binary compatible at the data layer. You know, the C++ class has a bunch of methods to operate on the class, and in D we can also have a bunch of methods to operate on the class, and they don't know about the two. Neither side knows about the other, but it all just works because they have the same data layout. And so this works well in cases where you've got standard layout structures and you're not doing anything weird in your like copy constructor or other things, or if you are doing something weird, that you make sure you do the same weird thing on both sides. The other 2 ways that we end up wrapping data types is using opaque pointers. And I'll give an example of this in just a second of, you know, my C++ code has the full definition of the implementation. My D code doesn't see the data layout at all. It just sees a number of wrapper functions for when I want to do operations on this type. Here's the C++ function I call. And the third option, which I'll also talk about a little bit, is creating conversion functions. And this is sort of a last resort for cases where we sort of throw our hands up in the air and say, this is kind of hard. Let's just take our C++ type and convert it into an equivalent D type when we need to pass it back and forth between the 2 languages. So using opaque pointers, say, for example, I have this coffee maker class, and I've spent a bunch of time in C++ building a really smart coffee maker that knows how to construct itself and brew some coffee and even has this fancy self-cleaning feature. So say I've got this class in C++, and I want to be able to brew coffee from D. And I don't want to re-implement all the code in D. So in D, what we normally do is we'll just define a structure. So up at the top here, this struct CVP coffee maker represents our C coffee maker object. So the D code never sees the full definition, what the data layout is, but I can store a pointer to a C++ coffee maker. And so in D, I define a D coffee maker class. It has all the same API, all the methods, and they're all just one-liners that call C++ stub functions that do the right thing. So in the constructor, I call my C++ coffee maker creation function, and then I get the result, because that's a CPP result object, and that checks to make sure I didn't get an exception thrown. Same sort of thing for my destructor, and then my brew coffee method, my self-cleaning method. So it turns out in practice, the bulk of our bindings, most of our bindings we implement, use this mechanism, use this opaque pointer case. In a handful of cases, we do a similar thing for being able to use D classes and D structures from C++. And this also works OK. There are a handful of gotchas around D classes versus D structures. Being able to wrap D structures like this is really pretty straightforward. Wrapping D classes is a little bit trickier because from a parameter passing perspective, an instance of a class in D is a lot more like a pointer to an instance of a class in C++. And you also need to be aware of garbage collection and how you manage ownership of that. So the third method that I mentioned here of how we do expose C++ data types into D is type conversion. So there's a handful of data types. Most of the time, these are like STL containers, where it's like, I've got a function, and it returns a map of strings to integers. And there's just no way I'm going to be able to define a binary compatible structure in D that's going to be compatible with my C++ map, because I don't even think that there is a binary, it's not specified in the C++ standard. Different STL implementations may lay out the data differently, and so I just won't be able to create a portable binary compatible interface. And if I wanted to use the opaque pointer API, that also just doesn't give me the flexibility I want. In D, I really want to be able to view this as an associative array of strings to integers. I don't want to have some C++ map type objects that I have to deal with. So in cases like this, we will end up writing a conversion function that when I implement my C++ wrapper that calls this native C get service counters method, it'll get back the C++ map, and then it'll convert it into a D associative array, and then I'll return it back. So of all these three mechanisms for wrapping C++ data types, using binary compatible structures is the most efficient because they just point at the same memory. The downside, it's the most fragile of the three of them. If someone in C++ goes and adds new fields, it's going to blow up in your face, like I mentioned before. The opaque pointers, there's a little bit of overhead here, right? Because if you looked at our coffee maker class, we had to create our C++ coffee maker object, and then we had this wrapper class in D. So we have an extra additional object here that we're creating. And we do have like another hop going through a function call to invoke them. The function call hop is relatively minor. It's that extra class object that ends up creating overhead for us. The benefit of this, it's pretty straightforward. You get a lot of flexibility, and it's not anywhere near as fragile as trying to define binary compatible structures. So with my opaque class there, with my coffee maker wrapper, the invocation of all those C++ functions was done, of all my C++ class methods, was done via my C++ stub functions. So those stub functions are unlikely to change. And if my C++ coffee maker class changes, the code invoking it is still C++. So it just does the right thing. It sees the source changes in the C++ file, and it does the right thing. So that's sort of a nice benefit for us. And the conversion functions, we really just do as a last resort. It's the least efficient of them, because if I had this big, huge map of strings to integer, like I mentioned, I have to pay a big cost to convert those into a D associative array. And it's really awkward to write that code that actually creates the D associative array. unit with a lot of like cross-language boundary calls to say like, hey, please create a D and associative array from me, because I don't know how to do that in C++. And then, hey, please go add these elements to it. So it ends up with really awkward code, and so we try and avoid this as much as possible. So I already talked a little bit about templates. So we can't instantiate C++ templates from D, but we can use the already instantiated template types. So in the case of our C++ result type, those were just binary compatible, and we knew whenever we had a D version of our template instantiation, there's also a corresponding C++ instantiation of it. We also have a few cases where I know my D code only cares about this one instantiation, so I'll create an opaque pointer wrapper around this one instantiation of my C++ template. And so we will do that in some cases as well. And so this works as long as you've got your C++ stubs on the other side that instantiate your template for D. So that's all pretty straightforward up until now. We do have a number of other cases where we've got some APIs where I've got a C++ base class, and you can derive from it in C++ and override some virtual methods. And what if I want to be able to do the same thing in D? So I've got some C++ base class. Now I want to have a D subclass of that. How do we achieve that? So if our C++ base class was pure virtual, we can have a D interface, and we derive from our D interface, and things sort of work. It turns out in practice we have some of those. We've also got a number of classes of like callback objects that are mostly pure virtual, but there's like one or two little things in there in the base class that's not completely pure virtual, right? Like, so we've got a number of callback classes where, you know, okay, you want to be notified when there's data ready from a socket, and so here's a callback object that you'll derive from and implement, like, hey, here's data, or you got an error. But it'll have a little bit of logic in the destructor. It'll point to who it's registered with, so that if you destroy your callback object, it automatically unregisters itself. So you don't end up with like someone trying to invoke a callback that no longer exists. So we do have a number of C++ base classes that aren't really pure virtual, and we can't use the D interface trick. But nonetheless, we still are able to call them to implement the features that we want with the appropriate wrappers. So the way we achieve this, if we've got our C++ base class, we can define a corresponding base class in D that's got the same API. And then we can build a special C++ subclass that knows, hey, whenever I get called and whenever any of my virtual methods gets invoked, I just point to a D object. And so I'm going to call back into the D code and ask the D base class to invoke its subclass. So now this lets me define a subclass in D. And when I want to instantiate that, I end up creating its sort of parent C class object that creates this special C++ subclass over here, pointing to my D object. And so now when my callback is invoked, it calls the C++ virtual function. That invokes the C++ subclass over here, which calls into my D code and down into my D subclass. And generally in these cases, we also end up having our D base class point back to the C code. Because if there are other data members or non-virtual functions or any time you want to invoke something on the parent class, this lets us have the D subclass call back and invoke the C++ parent class methods. So that's sort of all the main patterns we're using today in creating D bindings to all of our C++ classes. So the good thing here is we have been able to sort of, all of the patterns that we needed to so far, we've been able to create wrappers for that work pretty well and expose pretty decent looking D APIs into our C++ code. So let's talk a little bit about tools for this. So there are a number of tools around for translating C header files into D. So the ones that I've been aware of, it sounds like there is Swig support as well for doing some of this. So there's H2D, which has been around for a while. But it seems to be Windows only, and as far as I can tell, there haven't been any updates in quite a while. There was a tool called BCD, which also looks like it hasn't had any updates in 6 or 7 years. There is, however, a tool that still seems to be maintained called DStep. And so we've looked into this. DStep is written for C and Objective-C, and so it can translate C and Objective-C headers into D. It doesn't really have support for C++ and C++ classes, though, which is the main drawback for us. It sounds like if Swig has some support for this, then we can also look into using Swig as well. For generating C declarations from D, there's also more recently a tool called D to H. So this will let you take a D file and generate C and C++ headers, so your D code can access, so your C++ code can access your D structs. So this also is out there. For us, most of our use cases are invoking existing C++ code from D, so we aren't using D to H much internally yet. So the tools for C++. For us, this is a little bit of a to-do. Up until now, most of our bindings have been manually written, but we do think there's a strong possibility here for building better tools and for helping us automate this process. So we do have some helper libraries. Like I mentioned, we have the CVP result class. We have a handful of other small things. And we'll work on publishing those and getting those out to the open source mailing list. Up until now, they've sort of been internal, and we didn't release them initially. Just we wanted to make sure they worked well for us internally, but we'll definitely get on getting those back to the community. So we think there are a lot of opportunities to actually implement tools that we can automate the binding generation. Up until a few years ago, parsing C++ was really hard, but we do have the Clang AST these days, and DStep is using the Clang AST internally. So this lets us, Clang does all the heavy lifting of parsing the C++ code, and then spits out an abstract syntax tree for here's the actual syntax of the C++ file. So we don't have to do all the crazy parsing of like, this is a template, and now in C++ 11 it's a, these two angle brackets next to each other are templates. They're not a stream operator, and all the other crazy things about, C++ parsing. So there's much better tooling for parsing C++ and being able to do work on the result of that nowadays. And so far, our bindings are very mechanical. So I think there is a lot of opportunity here for taking those manual steps, those manual mechanical steps, and turning them into automated tools. So there are still a number of challenges, though, for building tools that can just automatically take C++ code and generate D bindings for it. Like I mentioned, we have these three ways that we tend to wrap C++ classes for D. So it does seem like there's some human intervention that's going to be required there in a lot of cases to say, hey, for this C++ type over here, I want you to generate a binary compatible structure for it. And you probably won't be able to generate the methods, but you'll be able to get the data member access for it. And for this structure over here, I want you to generate like a wrapper using the opaque pointer wrapping mechanism. Or for this structure over here, don't worry about it, and I'm going to have to write some sort of manual conversion. I think it might be difficult to write those manual conversion functions for like, hey, how do I take a C++ standard map and convert it into an associative array in D? I think there may always be some manual steps required there for those pieces. So I think there's some manual input that's required for those pieces. The namespace mapping, I'll have to take a look at the new namespace support now in D, but how do I want to map my C++ namespaces into D package layout? Because for us in our case, I don't know that it makes sense to just necessarily take our existing C++ namespaces and convert them one-to-one to D. And then macro handling is another sort of challenge for tools that have tried this in the past. I think there's some possibility for saying to have some human input to say, yes, I want you to generate bindings for these macros over here that are function-like, but punt on these others. So that's just a challenge. But I think a lot of these can be overcome. One of the things that I want to talk about, though, is sort of some tooling workflow. So I've mentioned this sort of imaginary right now tool of CVP to D. Whatever this is that we end up building to convert C++ code to D, whether it's extending DStep or Swig or something else, if we have something that reads a C++ header file and generates D from it, if you look at a lot of the discussions that have happened in the past, a lot of the recommended stuff is, hey, you run the tool, and then afterwards, it's not always going to generate code that's exactly what you want, so you have to do some manual editing of this file after the fact. So I think this is a little bit unfortunate for our workflow, because this means that every time the C++ header file changes, you rerun your tool, and you need a human in this workflow to edit the file again. So anytime any change happens to the C++ header file, there's this manual step that has to happen again, which is really just, I think, infeasible given the rate of change of our C and C++ header files. We can't have someone rerunning this process, doing manual editing, and checking in the final result each time. So we'd like to see a tool that instead of having this human input on the right-hand side, has the human input on the left-hand side as some additional input file. That if we can generate an instruction file that says, hey, parse this CPP file, and this class generate binary compatible bindings, and these classes generate opaque wrappers for. We think that this way we can deal with a lot of changes to the C++ header files without having to go do a lot of manual input each time. And it'll only be really big refactorings that require changes to this instruction file down here. So that's sort of what we'd like to see. We're thinking of building some of these tools. But hey, if there are also lieutenants that want to step up and help out too, that's great as well. A couple other tools that we're looking into and interested in building. One is an ABI checker. So that at least we can get some sort of warning or heads up if for our binary compatible structures, that if they aren't actually binary compatible structures, we'd like to know that at build time, not at runtime when we silently corrupt memory and have some other sort of problem. So I think there's a good possibility here to build a tool that's going to look at all your .o files and tell you when they aren't actually binary compatible. And there are actually some tools out there that exist already for checking ABI compatibility between C++ dynamic libraries to tell you, like, hey, you've got a C++ dynamic library. Between these two versions, your ABI has actually changed. And we think we can probably reuse some of those to check for ABI compatibility between the C++ and the deep components of a single binary. So we think there's also a lot of stuff that can be done here to at least tell you so the developer doesn't have to spend a lot of time scratching his head and figuring out, like, OK, I know my code blew up. Where did it blow up and why and what caused it initially? So just to wrap up, a little bit about our experiences so far. We have been able to build nice, easy to use, native feeling D wrappers for all of our C++ code that we've needed to do so far, even for things like I want to create a D subclass of my C++ class. It is still a pretty manual process. We do think there's a lot of opportunities for building tools. But it's pretty unpleasant when you have to debug, like, why is it going wrong and why is it not compatible. And I guess one other thing that I might mention here, I don't know if there's been any progress on this. There's been a bug in DMD for a while where even if you get your binary compatible layouts the same, DMD has some issues on x86-64 where the parameter passing conventions aren't really the same. So even though you got it right, if you pass a small structure from D into C++, DMD always passes it on the stack. And C++ expects it to be passed in registers. And so then it also blows up in your face as well. So I think there has been a little bit of movement on that recently. GDC and LDC both do the right thing here because they're just using the normal GCC and Clang backends. But so far, up until now, we still have a rather limited number of of developers in our Facebook infrastructure using D on a daily basis. Even for me, on most days, I still don't end up spending most of my time doing coding in C++ or Python rather than D. But we've had a positive experience so far. I think there's a good possibility here to start building better tools to have really good integration out of the box so that we can get better traction and start making it easier for more developers to build services in D and get the same functionality that they would if they built their service in C++. Cool.
Thanks, Adam. Awesome. Walter.
Hi. You talked about the manual intervention step in CPP to D and providing an instruction file to try to automate that. Another approach is to modify the C++ header so it's translatable and have CPP to D error out if it fails, so that you know if it's translatable or not. For example, you can replace hash-defined macros that define constants with const declarations, for example.
Yeah, so modifying our C++ header files to be more amenable to automated tooling is one option. I think there will be some challenges there. Like we'll probably get some pushback from C++ developers, who own those libraries and may have valid or not reasons for pushing back to say no, I like it the way it is. The other thing that I think is a concern for us is third-party libraries. So in a lot of cases, we'll want to either wrap a third-party code directly or wrap our header file that then invokes a third-party header. And so in some of these cases, we'll need to wrap data structures that are from third-party libraries that we could go and edit those third-party header files, but it's more ideal for us if we stay in sync with the upstream headers. We could try and push those changes all the way back to the upstream project to say hey, could you modify this header file from whatever upstream project, whether or not it's OpenSSL or whatever library, push it all the way back up the chain. I think it's just going to be a little bit less friction for developers if they can have this instruction file for cases where it's hard, technically or non-technically, for whatever reasons it is, to make those changes in the C++ header files.
I have two questions, actually. One of your slides, you had the CPP result struct in D, and you had the disabled post-split constructor. I was just wondering why.
Just because the CPP result is always constructed from C code. This result. Yeah. So CPP result. This is always used. This is when you've got your D code calls a C++ function. The CPP result contains the result from your C++ function. Success or exception. One thing on this exception info object, on the previous slide, I don't have the details of this exception info here. I guess what this, you probably, if you wanted to, you could build the constructor. Oh, sorry, this is the copy constructor. I have to look at the details of what this in that exception info. It's possible that we could implement the post-split constructor here.
I was wondering if it was necessary or not, because it kind of reminds me of the boilerplate you need in C++ of equals delete all the time. And I was like, well, this is D. Do we have to do that? So I was just wondering.
Yes, it's also possible. I have to go back and double check. It's possible I might have copied this wrong into the slide. We definitely disable the normal constructor.
Because you want it constructed on that side. So.
Yes.
My second question was, with all those indirections, when you have those wrappings, do you suffer with performance? Is that a concern at all?
So I haven't done a lot of benchmarks yet. Most of the performance results we've done so far, and which hasn't been a ton, these aren't the things that show up at the top of our performance charts. It's mostly been GC code so far. But just from my experience in C++, I don't expect there to be a huge overhead for doing the function call. In all these cases, they're not indirect function calls. They're not virtual. I know this address right here I'm jumping to. So as long as it's predictable, at least in the C++ side of things, that tends to be fairly low overhead, a couple of nanoseconds for us.
OK, cool. Thanks.
Relaying, while we transfer microphone, relaying a question from the online stream. Did you need to disable the GC to do all this work?
Did we need to disable the GC? No, we don't disable the GC for any of this right now. I mentioned briefly this. We do have a couple of cases right now where we are calling back from C++ into D, like a couple of the cases for these callbacks and other things. We do have a couple of cases where we've got a D class, we pass it into C++. So far, we aren't doing anything where we actually need that C++ code to maintain a reference to that object. Every time we pass in our D classes into C++, so far, we call the C++ function. It only temporarily needs it until it returns, and then it gives it back. So there's no real GC interaction here. So we aren't disabling the GC right now.
Just for completeness, there's another conversion tool in the Visual D project in the C2D folder. So it's in the programming language GitHub Visual D project.
Okay.
It might be yet another subset of headers that can be converted with that one.
Do you know the name of that tool? Is that separate from C2D?
No, it's a separate tool. So it converts it results in a separate executable, but it might be very dedicated to Visual D, although I've used it for some unrelated headers.
Okay, I'll take a look. I know of the C2D that I think was from Walter that was Windows only.
Yeah, this is C with the number.
Oh, C2D, I see, with the number. Got it. Okay, I'll take a look at that one.
All right. Let's give Adam another hand. Thank you. And chat him up if you want to find more about it all. And let's take just 5 minutes of break.